Okay, welcome to this session where we're going to introduce a pretty new idea called Residuality Theory, which is going to help us as architects and software engineers make decisions in conditions of uncertainty. So, a little bit about me. I've been in the business for 20 years, and right now I am a PhD candidate in complexity science and software engineering. And the focus of this session is going to be the subject of my PhD research and this paper, Residuality Theory, Random Simulation, and Attractor Networks. So we'll start off by defining the problem. Why are we even talking about this? What is the issue that needs to be solved? Why do we need to do research? Why do we need to think about this? Why is software architecture so difficult? Why is it so hard to articulate our decisions, to describe to junior architects and junior software engineers how we've arrived at those decisions? Why do we get so many non-committal answers when we try to figure out how did we arrive at this particular solution? And before we dive into that, we need to understand a few concepts. And the first concept is that of ordered systems. And this little box here represents a software architecture. And a software architecture is an ordered system. Okay, so it's got a relatively small number of components. It can be tested. It behaves more or less the same way over continuous cycles of testing. And we can predict its behavior. And it's based on mathematics and logic. It's essentially a machine. And what we do with this poor little innocent machine is we take it and we deploy it into reality, into a business reality, and that business exists in a market, which exists in a society with all of the economic and political conditions that exist in that society. And that is a disordered system, where we can't predict what's going to happen, where we don't understand what the potential futures are in that system. And the result of this is, as architects, that we have to spend time inside the ordered system making decisions about software. And we are all very well trained in that. We learn that at university, we learn that across the course of our careers. How many components should there be? How do we break them down? How do we test them? How do we deploy them? But as an architect, you've got to make those kind of calls. You've got to think like that, but you've also got to move outside of the ordered system and into the disordered system, where there are people, and say, what's happening here? What are the potential futures in this situation? And then you've got to bounce back into the ordered system and do some work in there and change the structure, and then you bounce back out and you talk to more people and you learn more things, and we bounce around between the ordered, simplistic, mechanistic world of software and out into the disordered world of human society and business all of the time. And as an architect, we have to constantly move between these two worlds. And as we do that, it's very, very easy to be confused, because in the ordered system, there's a set of tools and ideas and philosophical underpinnings that allow us to act in that world. And they're very much based on mathematics and logic. In the world surrounding the system, the human-centered world, those things don't hold. And if we try to treat that world like it's a machine and use the same tools, then things go very badly very quickly. And the fancy word for these kind of systems is hyperliminal systems, and that's just a fancy way of saying that we as architects have to constantly move in transit between these two worlds. And that allows us to talk about the actual problem that software architecture is trying to solve, and that is the problem with X. So we take this structure, which we as architects decide what that structure is, and we place it into this complex bubble of the business environment and the social environment in which it must live. And as soon as we do that, as soon as we deploy to production, things start to happen in this external environment, things that we cannot possibly predict or know ahead of time or control. And these things pop up all the time. Sometimes after we've put it into production, sometimes before you get to the end of your first sprint, these things will pop up and surprise you. And when that happens, they stress the architecture. They cause it to crumble. They make a mockery of our structural decisions. And this is an incredibly difficult problem to solve because all of those X's in this huge external system, there's too many of them. We can't write them down, we can't map them, we can't model them. So what we do to solve this problem is that we shrink the environment and we use tools like requirements engineering and risk management and all of the tools that you've learned over the course of your careers. And what we do is we make everything smaller. We shrink it. And that's a much easier reality to work with because now we're working with a much smaller number of X's, a much smaller reality. And this reality is very often an expression of the bias of the most powerful stakeholders in the project. But the problem doesn't go away. Sooner or later, there will be an X that pops up that causes the structure that we've decided upon to crumble. And so essentially what I'm saying here is that the job of the architect is to build a system that will survive an X that's going to occur in the future. And we don't know what that X is, we don't know when it's going to occur, we don't know why it's going to occur, we don't know anything about it. And when I say it like that, what I'm essentially saying is that the job of the architect is impossible, which is, not very inspiring. And so what I'm actually saying when I say that is that the job of the architect is to work with uncertainty. We have to build a structure that's going to be able to at least survive in some fashion in an environment where there's a great deal of uncertainty. And it turns out that there are other people who've been thinking about this outside of software engineering and computer science. And those people form a kind of shaggy discipline, which is referred to as the complexity sciences, which is a transdisciplinary thing. So you've got biologists and physicists and mathematicians, and disappointingly few software engineers working on the problem of complexity. And complexity is something that gets discussed a lot these days in architecture circles, but people tend to find it a little bit too abstract, a little bit too hand-wavy. It doesn't really deliver. There's a lot of nice words and nice concepts there, but it doesn't really tell us anything concrete as software engineers and architects about how we should behave differently. It just more or less says, yeah, X is there. Things are complex. So a lot of the work that I've had to do then is to try and make the complexity sciences and software engineering relevant to each other. So we're going to look at a couple of ideas that I've plucked from the complexity sciences that will help us to understand, help us to look at complexity science through the lens of a software engineer and software engineering through the lens of a complexity scientist. And that brings us to something called residuality theory, which at a philosophical level is very, very simple. What residuality theory says is that there is a system that looks like this, a bunch of nodes and links between them. It's a network, which is a very common way of describing these systems. And what we're saying is something is going to happen in this network, and we don't know what it is, and we don't know when it's going to happen, and we don't know exactly what impact it's going to have. And when that something happens, it's going to damage this network. It's going to damage the system in some way. It's going to change it. And this thing that's left over, the leftovers here, we call that the residue. Residue just means whatever's left over. And then the next thing we can say is that something else is going to happen in this system, and that's all we can say. We don't know what it is. We don't know when it's going to occur or the impact it's going to have. But we can say that the future of the system is a function of this residue. The next step in the system's life cycle will be influenced by that residue, and it will take on new nodes and new links, and it will change over time, but that residue will impact it massively. And as architects then, as software engineers, as people who are responsible for software structure in these hyperliminal systems, what we're saying is that we cannot predict what's going to happen and when, but we have control. When we make decisions about structure, we have control of the structure of the residue. That's all we can do. And so this changes what we are actually doing as architects. And so what we're doing now is not construction. We're not building something anymore. It's deconstruction. We're describing how a thing is going to fall apart. And it's a completely different perspective when we look at it from the perspective of residuality theory. The next thing that we have to do is to look at software from a complexity perspective so that these two worlds can meet. And so how do we describe software engineering as complexity scientists? And so I've plucked a couple of important ideas from the complexity sciences, and we're going to look at software. And so the first tool that we're going to use is the concept of random simulation. And this might be familiar to some of you who are doing machine learning, deep learning and things as a Monte Carlo simulation. And what we have is this square, and the only thing we know about this system is that the square is of side x. Inside the square, we have a circle, and we want to know what is the area of this circle. And we've all been trained, as you know, we've all probably all in here, there's a lot of people who've studied mathematics to a fairly high level, and we know that the area of the circle is pi r squared. But we don't know what r is, and we can't ever know what r is in this particular puzzle. And so what we do instead is we simulate the environment. What we do is we throw a dart at the shape, and the first dart, as you see here from this little white dot, hits the circle. The second dot misses the circle and hits the square. And based on that evidence, I can say that the area of the circle is half of the square, which is x squared over 2. That's probably not correct. It's a very small sample. But I throw a lot of darts at this thing. Eventually, and it's been shown many times, and you can Google this and find little simulators that solve exactly this problem. It's been shown that this is an incredibly accurate way to figure out the area of the circle. And you don't need to know any of the geometry of a circle in order to be able to solve this. And so you can solve this for all kinds of weird shapes inside the square of side x. And so random simulation is a standard technique that we use when something is deeply, deeply uncertain. When we don't really know what's going on, we can't measure everything. And if you think about the techniques that we use when we build software systems, they are essentially random simulations. When we gather requirements, a random person asks random stakeholders random questions at random times, writes them down in a random order. It's a random simulation of the environment. We've worked for far too long in the belief that requirements specifications are actually truth or represent something real in the world. The same with risk management, the same with estimates, the same with planning, the same with strategies, the same with patterns. All of these things are random simulations of the environment. And the way that we get this to work as architects is we do lots and lots of these random simulations and give them all these different names, and then we look at the tension between them in order to solve problems. The second concept from the complexity sciences, which is really important to us, is something called Kaufmann Networks, which were developed in the 1960s by a biologist called Stuart Kaufmann. And Kaufmann networks are random Boolean networks. That means that every node in the network is a Boolean. It represents a 0 or a 1. It can have two states, a 0 or a 1. And so a good way to think about this kind of network that I'm showing you here is a series of light bulbs, because it can be on or off. And every node in this Kaufmann network has a little algorithm that lives inside it. And when that algorithm executes, it decides randomly, am I a 0 or am I a 1? Is this light bulb on or is this light bulb off? And Kaufmann built this as a computer simulation, and a system like this has a number of states, and that number of states is always 2 to the n. So there's 2 to the n possible states. When Kaufmann ran this experiment, he let n be 100,000, which is 2 to the power of 100,000 possible states in the system, which is a greater number than the number of atoms in the universe. So if that's your requirement specification, that's a big, big document. Then he did something really interesting. He started to add links between the nodes. And these links allowed one node to tell one other node what its decision was, whether it was on or off. And it took that decision as input to its own little algorithm so that it influenced it in some way. And he found that at a certain level of adding these links between the nodes, connecting the system, that the number of states fell from 2 to the power of 100 to 317, which is roughly root n. And if we're working with complex systems, that's incredibly good news. That's a lot less to work with. And he called these states that the system kept, he noticed this first, that the system kept going back to the same patterns over and over and over again, which would mean the same pattern of on and off lights, that you would see the same thing flashing over and over and over again. And he called these states attractors, because it seemed like the system was attracted to these states, that it wanted to be there. And then he started to look at some variables that he thought were very important in these kind of networks. And there's 3 variables here that are very important. The first variable is n, which is the number of nodes in the network. And Kaufmann and a bunch of other people, including last year's Nobel Prize winner Parisi, did some work on showing that the higher n is, the greater the number of attractors in a system. So the more nodes you have, the more states that the system is going to circle around in its life cycle. Another variable that was really important is k. And k is the maximum number of links that a node has in this system. It can be the maximum or it can be the average, or you can use both. But it gives us an idea of how interconnected is this system. And in this case, k is 3. K max is 3. And he noticed that if k is very, very low, then the system is very rigid, very stable, very ordered, very boring, and very likely to die quickly in a complex environment because it can't change, it can't move. And he noticed that if k gets very, very high, 4 or 5, then the system becomes incredibly unstable. The number of attractors grows enormously, and no one knows what's going to happen in the system. Whenever you change something and wherever you introduce stimulus to the system, anything can happen. It becomes deeply unpredictable. And a third variable he found is called P, which is bias. And he found that if we take this node here, and we say that it has a probability of 0.5 to send a message this way, and 0.5 to send its message this way, then we say that this node has no bias. It's not biased to one path or the other. But if we take this node up here, and we give this a probability of 0.95, and this of 0.05, then we say that this node has bias towards this path here. And what he found was that if you raised k, and you got this massive number of attractors, and the system started to be uncontrollable, then you could raise p, and the system would settle back down. Now, this might sound like something that's incredibly new to you, but if you're a software engineer, you've been working with these variables, n, k, and p, right through your entire career. This is nothing new to a software engineer or a software architect. N is the number of nodes. How many components should there be in this system? K is the links. How many links? How should these components be linked to each other? We've all been thinking about these things, and we've, as an industry since the 1960s. How should these things be linked to each other? How do we couple them, decouple them? And bias turns up in software engineering as contract design, schema design, interface design, making sure that when a component receives a certain stimulus, it responds in a predictable way, that we respond to errors in the same way. All of these things, most of service orientation, is about introducing bias to the system in order to lower the number of attractors that the system will visit. So what we can conclude from this is that every software project is actually a combination of a random simulation of the environment followed by an NKP analysis. Every software project that you've ever worked on is a combination of these two things. Now, we're not taught the complexity science at university, so we don't express things in this way. But it's very obviously true. This is what's happening in our projects. And so when we combine these ideas with residuality theory, what we can do is we can make the random simulation more random and the NKP analysis explicit. And so one of the problems that we have when we're doing random simulation is that we're limited in that randomness. And we're limited by bias, the bias of our stakeholders, the bias of ourselves. And we talk about probability, and we use probability and what we believe is likely to limit our random simulation of the environment so that it's not really random. And what we tend to end up doing is finding a lot of dots that are closely clustered together, because we say things like, keep it simple, stupid, you ain't going to need it, or that's never going to happen, as our business stakeholders say. This is called the curse of high dimensionality, and it's a well understood problem in statistics. NKP analysis is something that we do, but it's not explicit. And we dress our NKP analysis up in a whole bunch of different types of language and ideas. So some people say, I use domain-driven design, or some people say, I use solid, or some people say, I use grasp, or some people are honest and say, I just make it up as I go along. But all of those people, these are extra layers that we've put on top of what's essentially an NKP analysis. We're constantly trying to control a network and keep it controllable and manageable. And so what we do now with residuality theory is we make the simulation more random. We help ourselves to be more random when we simulate the environment, and we make the NKP analysis explicit. How do we do that? Well, first we go back to our original problem, and we say, here we have this ordered, structured software system inside this complex, disordered human business system, social system. And now what we've learned is that all of these variables, all of these possible states, all of these things that might happen in this system aren't really relevant, because the system will consist of a number of attractor states, a number of states that it will continue to visit over and over again. And any business system will then cycle around its attractors as things push and pull on it, as things internally change in the business environment. And one of the things that we're guilty of as an industry is that we consistently build systems for one attractor. And that's that curse of high dimensionality, that little red circle, that you ain't going to need it, that's never going to happen. We're restricting the number of attractors that we need to think about in every single project. And so what we do is we simulate the attractors by telling stories. And so we come up with an X, a stressor. What can hurt this system? What would happen if a competitor drops their price? What will happen if there's a change in market sentiment? And that pushes the system to an attractor. And in that attractor, we can observe our architecture, our structure, and we can say that these two components are broken. They no longer work in this structure. So we change it. We add this green component, and we say, if we had this green component, then the architecture would have survived in this attractor. It would have survived this stressor. And then we take that, that's our residue, and we say, this is residue number 1, and we put it over here. And then we generate another stressor. And we do the same thing. We add this little orange component and say, this orange component is necessary to make the system survive in this particular attractor. And we put that over here, and we say, that's residue number 2. And we do the same thing again. And what we're doing is we're randomly simulating the environment with these random stressors, and we're producing these residues. And the result is that we have our original naive architecture when we didn't know very much about the system at all, and a whole bunch of residual architectures. Residues. And what we do is we combine all of these to produce a single architecture that will serve multiple attractors in the environment. And what we're actually doing here is we're using a mathematical fact about these systems to leverage that so that we don't have to do so much work. And it turns out that every residue that we would design will necessarily support more than one attractor. It doesn't have to, but it usually will support more than one attractor. And that's got to do with, if we think of n, the number of nodes inside our software system, which is very small, or it should be, and the number of nodes in the external business system, which is absolutely enormous, and we don't even understand half of them, or not even that. And so every residue points to at least a couple of attractors, and every attractor then can be reached for the business by a bunch of different X's. A bunch of different stressors can push the business system into that attractor. And all we have to do as architects then is identify one X, one stressor, which helps us identify this particular attractor, which helps us identify this residue. And it means that all of these X's will not affect our system. Our system will survive in those X's, and it will look like magic when this happens. It will look like our system is surviving a whole bunch of X's that we haven't designed it for, that aren't in any specification. Which is how all complex structures, our societies, our economies, our relationships, it's how all of them actually survive. And this, one of the things that we have to do to get away from this is to make sure that our sampling of X is random enough, that it's wide enough, that it isn't too limited. Normally when I ask very technical people to come up with a list of stressors for things, it's things like the disk breaks, the network goes down, the power goes out, the load balancer fails, but it has to be much, much broader than that. And one of the stressors that I ask everyone to use is this one. Giant fire-breathing lizards come up out of the North Sea and destroy Antwerp. What's your residue? Does your architecture still work? And at this point, people think he's lost his mind. What is he talking about? That's definitely never going to happen. Firstly, we should never say definitely, because we don't know anymore. But the point is that this is something that's extremely unlikely. And it's an X like here. And if I can say that I have a residue, my architecture will survive when these giant fire-breathing lizards destroy Antwerp. I've also built an architecture that's going to survive flooding. It's going to survive civil unrest. It's going to survive the failure of the energy grid. It's going to survive a pandemic. It's going to survive an invasion. All of these things can happen, as we've learned in the last few years. And so that's an example of, I've used one ridiculous X with a very low probability, but I've built a system that protects against a whole bunch of other things that might actually happen. And so what I'm doing with these stressors is I'm not solving for a particular X. I'm not interested in these lizards. I don't actually believe in them. What I'm doing is I'm finding the cracks. I'm finding the cracks in the structure of the architecture, and I'm fixing them with these residues. And so that's why it works mathematically. So here's an example to give you an idea of how this actually works in the real world. So we have a system. This is a slightly fictitious system. It's an amalgamation of a bunch of different projects. But it's a cloud-based system that takes care of a network, a global network of fast chargers for electric cars. The way it works is you drive up to the fast charger, you have a little key fob that you get when you register on the website. You hold up the key fob, a message goes from the charger up to the cloud, decides whether you're allowed to charge or not, and sends a message back down that says, yes, you can charge now. And this is a list of stressors produced for such a project. And there's a pattern that I want to talk about here. So stressor number 3 is what happens if the key fob stops working. What happens if it gets too cold, gets too hot, someone puts a magnet on it, a child eats it or something. It's not working anymore. What's the residue? Well, the residue is that someone's driven up in their electric car, they can't log in, they can't charge. They maybe have very little power left in the car, so they're not going anywhere. And they're parked in front of our asset, and they're not moving, and there's a queue forming behind them, and that's not good. And so we say, well, how can we change this? What can we do? What's the little green component that we need here? And what we come up with is automatic license plate recognition. Let's get rid of the key fobs. They're unreliable. People are going to lose them. They cause us issues. And so what we do is we build a system that automatically reads off the person's license plate, and we allow everyone to charge so that they can charge their car, because electricity back in these days wasn't that expensive. We allow them to charge, and we get rid of them. It's cheaper to get rid of them and send them a bill later on, and we might miss the odd one, but that's not a big deal. So we allow them to charge, and we invoice later on registration. The next stressor that's interesting is stressor number 8, and that is that somehow our chargers get damaged. and this will happen. People will drive into them. That's kind of inevitable. There's also a risk for vandalism as well. And so what we do is we deploy some form of redundancy. We have more chargers than we need. And we have security cameras which should encourage less vandalism over time. And the third stressor that's interesting is stressor number 12. And this is a problem with if you have car charging parks beside golf courses. People plug their car in and they go off and they play golf. And the charger's locked up for 8 hours or longer. And that, again, our asset is stranded. No one else can use it. And so what we did to solve this problem was we used something from another residue, which is a pattern we see happening a lot when we use this methodology. And we use a new idea, we invoice per minute. So the first 25 minutes are at a regular cost. After 25 minutes, it starts to cost more. After 50 minutes, it starts to cost more. After a few hours, the cost is astronomical. And at that point, we've taken something that was stressing our system and turned it into a profit center. So we say, do this if you want. We will make more money. That's good for us. What we've done so far is standard business development. It's not really that interesting, those three things on their own. The next stressor that I want to talk about is down here, is number 14. It's this thing called icing. And icing is something that started to happen in the United States a few years ago. ICE stands for internal combustion engine. It means a fossil fuel car. And because of the political tensions between groups in the United States, one of the things that started to happen was that people started to ascribe beliefs, political beliefs, to people who drove electric cars. And so they would say, if a person drives an electric car, they vote for the other side, and I don't like that. So what they started to do was they started to park their pickup trucks in front of the electric chargers just to annoy people. And this became a thing, a trend. And it's obviously very, very stressful for a company that has a large number of fast chargers for cars. But if you look at our stressor, our residual architecture that covers a bunch of different detractors because of these stressors, the combination of number 12, 3 and 8 means that, firstly, if you park your pickup truck in front of our charger, we have your license plates. We also have you on a security camera for a police report. We know it's you. And you're going to get a bill, because we don't care if you plug in or not. We're going to charge you for the time that you're sitting in front of the charger. And that means that for this project, this stressor, which is absolutely impossible to predict, this isn't the sort of thing we do or can predict, this system will survive. And this is what you start to see. If you use this methodology, as you move down through this list of stressors, you start to see that the system is able to cope on its own. And eventually you get bored. You won't be able to find anything new. You keep stressing it and stressing it and stressing it, and you can't break it. And that's when you know that you've maybe shifted things a little bit. And if you think this was a uniquely American problem, it's now turned up in Europe, where people have ascribed the vegetarianism and to ownership of an electric car, and they've decided to protest against this by shoving mincemeat into the chargers. Now, if you do standard enterprise risk management, there is no way on earth that you have in your risk register someone is going to stick mincemeat into my device. It's just not there. And that's the world we live in. The things are so interconnected, so complex, these ripples come from the business system, and all of a sudden you've got mincemeat in your devices. And architecture has to move with that. We have to be able to answer these unseen, unknowable stressors in our architectures. So the next step, once we've done all that, is something called contagion analysis. And contagion analysis means we're going to take all of these residues, which is a great number of architectures that may differ from each other, but mostly they're similar. And we're going to squeeze them all together in one single architecture, one single coherent architecture, without damaging their ability to survive in all of these attractors. How do we do that? Well, there's a few concepts we need to look at first. One is this idea of decomposition. So we all have our favorite methods of decomposing a system. Usually they look something like this. And we would look at this system and we would say that B is coupled to C and C is coupled to D. But this is a hyperliminal system, so we take this ordered little system and we place it inside this complex thing that we don't understand. What happens is an X, a stressor, will pop up. And what happens very often is that that stressor will surprise us. It will attack component C, and we'll have to rip it apart, rebuild it, rethink it, rework it. And it will also hit component G, and that will surprise us too. And in network science, when you have three nodes gathered like this, and there's a relationship between the stressor and C and a relationship between the stressor and G, we can say that there is a relationship between C and G. And what we're actually saying is C and G are coupled. And as we move through our stressors on our naive architecture, what we tend to find is an intricate spider web of this invisible coupling. And because it's not functional, there's no functional relationship between C and G that we're aware of, what we're actually doing with this stressor exercise is we're discovering non-functional requirements in a very methodical way, which is much better than going to our stakeholders and saying, what's your non-functional requirements? Because we all know how well that works, right? And so contagion analysis helps us find this hyperliminal coupling to make sure that when we squeeze things together that we're not missing things. And the first thing we do is we use, because networks are hard to draw, they're messy, it's okay sometimes, but usually it's better to express these things as matrices. The first thing we use are Gsnc matrices or design structure matrices, and this is a tool that they use at MIT, that they teach at MIT to people who build aeroplanes and spaceships to decide on component structure inside those things. And we look for patterns, and we just map functions, potential components against each other, and we put a 1 where there's a dependency and a 0 where there isn't. And then we look for patterns, like this little triangle. That's a sign that this is a fairly safe system to play with. There's not a great deal going on here. But then we start to see something that we call mirroring, where components have interdependencies. They're dependent on each other for some reason. Something's wrong here. If you add up all the ones in one of these matrices and divide it by the number of components, you get a value for K that we talked about earlier. And as this starts to happen, as you start to see interdependency, K is rising. This is dangerous. And we all know this. As a developer, you're looking at this and thinking, what's wrong here? Someone's messed up. It's either the developer or the business doesn't know what's happening here. Or we're trying to solve a whole bunch of different problems in one set of components when they should be split up. So we need to refactor. And this can get really bad if it's a new business, we don't really know how anything works yet. It can get really crazy. And there are businesses where it looks like this, and that's just how they like to do business. And this gives us an impression about how things are related to each other. And the final step then, once we have an idea of where dependency and interdependency exist in our system, and we refactor a little bit, then we use a final tool which is called Incidence Matrices. And an incidence matrix looks like this. We take our potential list of components or functions. We can do this at many different levels in the system. And we take a list of stressors. And what we do is we go through the thing and we set a 0. If the stressor doesn't hit that component, then it's a 0. The stressor and the component have no relationship. If the stressor does hit that component, then it gets a 1. And there's a bunch of things that come out of this kind of matrix that help us make concrete decisions as architects. Firstly, we get to see which stressors raise K, and all of these things, if you take the totals here and the totals here and add them together and divide it by the number of actors in this network, then you have a rough idea of what K is. And we want to get K as low as we can. And here we can see that this particular stressor, server failure, gives us a very high number of K. A lot of things fail when this happens. So maybe we want to think about how can we refactor this system in order to get that down, to lower that. Maybe we should have more than one server. Or maybe we should split our services up and let them run on different servers so that they don't all fail at the same time. And when we see a 1 here and a 1 here, then we know that there's coupling between those two things because the stressor's hitting both of them. And it's that CG relationship. So every time we see two 1s, we say that these two things are coupled in some way, and we go back to our adjacency matrices and we say that if there's no relationship in the adjacency matrix, if there's no functional relationship between these things, what we're actually doing is discovering hyperliminal or invisible coupling, and that means we're discovering non-functional requirements in the system, and discovering non-functional requirements in this way is actually how good architects do it. The good architects don't ask their stakeholders, what are your non-functional requirements, and put all the responsibility on them to express themselves in technical terms that they can never possibly do. Another thing we can do is we can isolate the components that are very, very susceptible to stress, like this stop charge command. And we can say that, well, this component needs to be looked after very much more than the others. It's very susceptible to being damaged. Maybe we can refactor it. Normally, when you see a component that takes a lot of stress all the time, it means it's doing too many things. It's got too many things going on. It's easy hurt because it's exposed to a whole bunch of different stressors and across attractors. It starts to crack. And so there are hints in here about refactoring. And the final thing we can do with this matrix is we can take all of the components that have very, very similar responses to stress, and they have the same sequence of numbers through the matrix. And we can say that these things are susceptible to exactly the same kinds of stress in exactly the same situations. And they can live together and die together because they're always going to, both of them are always going to get hurt by the same things. And what this is a component boundary. And this tells us that these two things get to live in the same component, get to live in the same box or the same process. It doesn't make any difference. And so from this really, really simple matrix, we get to make decisions about redundancy, we get to make refactoring decisions, we get to make decisions about sensitivity to certain kinds of stress, and we get to make component grouping decisions in a concrete way. So there was a guy called Paul Ralph who did a bunch of research in 2016. He went around and asked a whole bunch of software developers, how do you make component decisions in your code? And he did it under conditions of anonymity, so no one would ever find out what they said. And when he asked the question in this way, all of them were comfortable enough to say, we don't really know, we just kind of make it up as we go along. We can't explain it, we can't articulate it. And so this kind of work, this kind of thinking, allows us to be concrete about these component decisions. And the final thing that we do, and this would be the experiment that I'll run as part of my research, is that we take our naive architecture and we take a bunch of stressors and we use those, and then we use our contagion analysis and our matrices to produce a residual architecture. And these are two very, very different things. And then we take a second set of stressors that neither system has ever been exposed to before. So from the perspective of both the naive and the residual architecture, both of these things are X's, unknown stressors. And we work through the naive architecture and we expose it to every one of these stressors. And we say, did it survive? If it didn't survive, it gets a 0. If it did survive, it gets a 1. And we work through the whole list and we add up all the 1s and we call that X. And then we do the same thing to our residual architecture. We expose it to the red stressors, which it's never seen before. We run through, and every time it survives an unknown stressor, we give it a 1. If it doesn't survive, we give it a 0. In cases where both architectures get a 0, neither of them survive, the architecture that survives in the best way, in the way that's going to cost less to fix, gets the 1. And then what we can do is we can run this little calculation, y minus x, so is over s. So we're saying, is y bigger than x, is what we're asking. And this will give us a result between -1 and 1. And it's called the residual index. And if the residual index is greater than 0, then we've done useful work as architects. And as architects, being able to prove that you've done useful work, that will be the first time we're ever able to do that, which is a huge step forward for our profession. And this then is the focus of my research in doing this in a way that shows that this happens in a large enough group that is statistically significant, that this happens over and over and over again. And when I run these methods with students, when I run these methods with clients, they work every single time. And so a lot of my research now is desperately trying to make this feel so that the research paper is more interesting. So this is a big step forward for us as software architects. Obviously, once you've done this, there's a whole bunch of verification that needs to do. All of our classical systems engineering training has to be used to verify and validate these architectures. And so what I've actually presented to you here today is a brand new theory of software engineering. And not just a theory, but there are real concrete tools that any architect can use, any senior engineer can use. And it will help you to identify non-functional behavior, non-functional requirements. It will help you identify component boundaries. And it's based on research. And it's not just going to be another book with a pretty animal on the front. This is being put through the ringer. Okay. So, and this is compatible with everything else that you do. Unlike other methodologies, you don't have to throw anything away. If you're using domain-driven design, if you're using GRASP, if you're using something that you really believe in, you don't have to stop doing that. But you just have to learn to put your architectures through the ringer. There's a whole bunch of papers that have been written on this along the way. 4 or 5 academic papers, including a philosophy paper, much to the horror of my mathematics professor, on these ideas. But the one to start with is this one here on residuality theory, random simulation, and attractor networks, which is pretty much what we've looked at today. And so here are my contact details. If you have any questions, this QR code should take you to a link where we're going to hopefully be holding some workshops in Belgium next year. And this is Residuality Cat. It's fast becoming a mascot. And thank you for listening and coming. And I hope good luck with all of this.